when we don't have B2B communications, we assume that drivers are uncertain about the nature of the other driver's line changing maneuvers. So basically, they don't know if it is going to be a mandatory or discretionary line change. And model this behavior as a two-person, non-zero-sum, non-cooperative game under incomplete information. And also having incomplete information can be challenging because we don't know. Like here, we have two games, one for the mandatory lane changing and one for discretionary lane changing. And incomplete information means that we don't know which one to choose. So Harsanyi introduced a transformation. It's called Harsanyi transformation. This transformation introduces nature as a player into this game, and the nature chooses the type of lane change. In other words, it transforms the lag vehicle's incomplete information about the nature of each lane changing maneuver into imperfect information. Imperfect information means we know that with probability P, it's going to be mandatory, and with probability 1 minus P, it's going to be discretionary. What does that mean? Let me show you. So we talk about that we have two games. So if it is a discretionary lane changing, you have the game in the top. And if it is mandatory lane changing, it is the game in the top. And the payoff functions will be different for different games because, for instance, if it is a mandatory lane changing, the target vehicle has to change lane. This means that it might even force a lane changing because he or she doesn't have any other option. But that means that the payoff function will be different from the case that the driver is doing this for just to get into a higher speed. Okay. So we have these two games, and the complete information means that we can decide which one we want to solve as a lag vehicle. Well, keep in mind that target vehicle knows the lane changing type because he or she is the one that is changing the lane. The lag vehicle is the issue, and the lag vehicle doesn't know which type of lane changing is happening. So the lag vehicle does not have any idea which one to choose. So with Harsanyi transformation, we are introducing nature into this game. What happens is the nature starts the game, and if with the probability P, the game will be mandatory. With probability 1 minus P, the game will be discretionary. So this P can you can observe the data and come up with the kind of like the portion of the mandatory versus the discretionary lane changings. You can make it driver specific, or you can make it driver and situation specific. Well, in this study, we just looked at the data. So as I said, this is already a very complicated issue. We wanted to go as simple as possible to see if this approach is effective at all or not. So and then the driver A or the target vehicle will start the game. So the probability P is mandatory, probability 1 minus P is discretionary. And once it's mandatory, then we have the game. Once it's discretionary, we know which game we want to play. And with this, we can combine the two payoff functions, the two type of games, this one and this one, into this one. In other words, we are kind of like converting the two games of 3x2 into one game of 3x4. Which is harder to solve, but it is doable. And we can also observe the PM elements. So now, the second case is where we have, let me see what we have here. Okay, so I apologize. So the second case, the first case is when we had like a V2I communication. We didn't have V2I communication. When we have V2V communication, then just to remind you, we assume that drivers are lag vehicle knows what is the nature of lane change, and that means that you already know which game you want to play. So it's a two-person non-zero-sum, non-cooperative game under complete information. So in other words, we already know which either we want to go with Q series or R series here. So, up to this point, we formulated our game. The next step will be to define payoff functions. Truth is, you can get as fancy as you want about payoff functions. You can put 200 parameters there and try to solve it. The issue is you have to come up with a solution for calibration. And if you don't have a reliable way, it might take years to calibrate that many parameters with the current available techniques in game theory. So we said we wanted to start with a simple case and see if a simple case is effective. So the payoff matrices, we try to be as simple as possible in this case, and we have only 4 different parameters. So for the target vehicle, the table on the top, the first assumption, we assume that the payoff functions are relative to each other. In other words, when the target vehicle decides to not change lane, his or her payoff is 0. It's the driver's current condition. Of course, plus some error term, which is intended to capture unobservables here. When the target vehicle decides to change lane, depending on the behavior of lag vehicle, the driver can have different payoffs. If the lag vehicle decides to accelerate, the payoff function is a combination of 2 terms. The first term is the acceleration term that the lag vehicle needs to implement to avoid crash with the target vehicle. In other words, the target vehicle, before changing lane, the target vehicle will evaluate if it is possible for the lag vehicle to avoid crash. And the second term is the speed gain that the target vehicle can have. So the target vehicle will look at his current condition and the future condition and calculate the speed difference and see if he or she can get into a higher speed by changing that. If the lag vehicle decides to decelerate, we assume that the target vehicle will have the same concern. And the third case would be the case that lag vehicle decides to change lane. If the lag vehicle decides to change lane, it means that there's not going to be any conflict at all, and the only parameter in the payoff function would be the change in the speed gain for the target vehicle. So the target vehicle payoff function is simple. It gets more complicated for the lag vehicle. The lag vehicle, depending on the strategy of the target vehicle, can have different payoff functions. If the lag vehicle decides to accelerate, here, the first row, and the target vehicle decides to change lane, the payoff function will be the acceleration that the lag vehicle needs to implement to avoid crash with the target vehicle. If the target vehicle decides to not change lane, it's going to be the same acceleration. However, in this case, instead of considering target vehicle as the new leader, the lag vehicle will consider the old leader. Okay. When the lag vehicle decides to decelerate, well, the deceleration has to be comfortable for the driver to give way. And the comfortable deceleration that was used in the literature by few researchers was negative 3.05 meters per square second. And it was the case for both. It was the same for both of the cases that target vehicle decides to change lane or not to. And finally, when the lag vehicle decides to change lane and avoid the conflict, the lag vehicle will start a new game with a new lag vehicle. So the lag vehicle becomes a target vehicle, the new target vehicle, and there's going to be a new lag vehicle. So, and then they can start to play the same game. So, however, we put a limit on it. We decided that the new lag vehicle cannot change lane. So the new lag vehicle can only accelerate or decelerate. And the old lag vehicle, which is now trying to change lane, will have either of these two options and these payoff functions. They are the same, so we have only one. Okay. So now we have the gain, we have the payoff functions. It's time for us to calibrate it. So we use the method of simulated moments, or MSM, to calibrate the system. So how does this work? I forgot to mention that all these error terms in the payoff matrices have normal distribution. Okay. So the MSM uses a Monte Carlo simulation-based approach to calibrate it. For all parameters in the model, okay, we call it theta here, and in the payoff matrix you saw the eta. So they are the same. So the theta is for a general payoff matrix, not a simplified version. So for all the parameters in the model, what we do for every single one of them, we start with a Monte Carlo simulation. We draw a random number of a normal distribution for the epsilon. We formulate the payoff matrix. We solve the game and find the Nash equilibrium. Once we do, we wanted to have a kind of like a strategy selection approach. In strategy selection, we assume that we want to use a logic type selection method. So we have a beta here, and based on that, we can calculate the probability of selecting each Nash equilibrium. We also have observables. So no, observed data. So we compare the difference between the observed data, what we actually observe, and the probability of selecting that specific strategy. And we do this, we sum them together for all the observations for every combination of the parameters. Once we do that for all these cases, we pick the one that gives us the best results. In other words, this is an exhaustive search. That is the issue that I mentioned. So if you put too many parameters in your payoff matrix, you have to do this too many times, and that can take a lot of time because solving Nash equilibria is not an easy task. We're using Gambit. It's an open source tool to solve the games, and you can kind of it's a Linux-based tool, and you can incorporate it in any of the Linux tools that you have. So now, once we do this, so to do the calibration, we decided to go with ngsim data. We used the ngsim US 101 data set from 750 to 805, and we did the calibration. So we came up with the a few important things here. First of all, we observed the length changing behaviors. Second of all, we excluded the movements from ramp into the highway as the mandatory length. We exclude those from the analysis because the behavior of merging into the highway is different from the behavior from going from a highway into the ramp. So the mandatory lane changing are related to the movements for the vehicles that are going from the main lines into the off ramp. So now this is the calibration results for if we have the 4 data and the data that we have, and you can see the mean absolute error is pretty high. It's about 0.4. For mandatory lane changing, it is a lot better. One of the reasons is the mandatory lane changing has fewer observations here, so the error can't go that much. And we had a lot of dispersion lane changing maneuvers. But it's fine because this calibration method is probabilistic in nature, and we're using Monte Carlo simulation. So if you want to get the better results, you have to do this like, I don't know, 100 times, and you probably get a better mean absolute error. But I'll show you that even with these parameters, we could get a very, very good representation of reality. So next step for us would be to simulate the model. So we can't really assume that drivers will solve a game every time they want to change lane. That really doesn't make sense. So we looked into literature of learning games and how people play games in reality. And one of the very first models in this area is called fictitious. Okay, it's one of the very first models and one of the effective ones. And there are a lot more fancier ones, but as I said, we want it to be simple and see how we can deal with this. So for this simulation, the driver comes in with some knowledge, with some experience, okay, of his or her previous strategies that worked for the driver. So the whole process will go through a decision time. In decision time, we assume that has a normal distribution. So at the start point, the driver, based on the experience, chooses a strategy, the target vehicle. For instance, it chooses to change lane. And then it observes the strategy of the other vehicle, of the lag vehicle. If the combination of these two results in a Nash equilibrium, then the drivers execute the decision. If not, they took this as an experience and go back and select another strategy based on the observations. If they become, if they come up to a stable condition within the decision time, they execute the strategies. If they don't, if we reach a decision time, they execute the latest strategy and keep everything, in both of the cases, keep everything, all the observation as an experience for the next lane change. So there's an experience involved here, and drivers are getting more and more and more experience. So one of the deficiencies for this is you have to have some sort of warm-up period for your simulation to give drivers some kind of like learning process, learning time to adapt to the system. Or you can give it as a predefined set. So, but we also need a sort of simulation for the car following model. And the car following model that we developed at Northwestern had 3 different elements. I'm going to talk about only 2 of these elements: the no automation, not connected cars, the regular cars, and the no automation and connected cars, the ones that have V2V communications between them. And we are going to use these 2 cars to simulate the environment that I'll show you in the next few slides. For the case that we have only regular cars, the system is probabilistic in nature, and our perception of surrounding traffic conditions becomes subjective. Our reaction time is high, safe spacing high. We tend to stay away from the other vehicles. We have, and it's very likely to have crash. We use the same model that we developed in 2011. It's probabilistic. It can simulate crashes endogenously. There's no need to exclude them, and it's recognized different regimes for congested and uncongested regimes. It's recognized that drivers have different perceptions with different behaviors in congested versus uncongested regimes. The second case for the V2V communications, when the connected cars, then there's V2V communication between 2 cars, then the perception becomes more accurate, the behavior becomes deterministic, the reaction time is lower, the safe spacing is lower compared to the previous case, and it's very unlikely to see crashes or high-risk maneuvers because this system is will be designed to warn the drivers about the high-risk maneuvers, and we use the intelligent driver model to model this behavior. When we don't have V2V communications, of course, the system will go back all the way to the no automation, not connected case, and you're going to simulate it as probabilistic, the same way as we are simulating the regular cars. So I'm not going to cover the other types. I'm going to go directly to this the simulation results. To test all these modeling frameworks that we presented, we decided to simulate a real segment. We took a segment in Chicago. It's I-290. Eastbound toward downtown. And we simulated this for a morning peak time. This is not the most congested highway in Chicago, so it doesn't come to full stop in the morning, most of the time at least. And the good thing about this is it has a fairly reasonable volume. It has a high flow rate, but it doesn't come to full stop. So we are going to see some normal type lane changing, not the force, not the ones that we see in a very, very congested road with the traffic almost at full stop, when people try to force their way in. So that's why we chose this line. This segment is at 3.5 miles. It has 4 on-ramps and 3 off-ramps, and we try to simulate this behavior here. So this is the simulation results. On the top left here, you see the actual information, the actual time, the actual loop detector data. Okay, from 7 to 8:50, to 8:30, sorry. And this area here, the bright area here, is where we simulated. We simulated about 10 minutes with this model. And you can see there is an on-ramp between 2 and 2.5 here, which creates a lot of congestion. There's another on-ramp here with less flow rate, but there's a slow traffic here as well. So this is a pattern in this 10 minutes that we simulated, and we got the same flow rate into the market total simulation tool. First, we simulated the gap acceptance model. For the gap acceptance model, you can see that there is a congestion at the same location, pretty much. However, there are more congestion happening on another on-ramp And also the congestion here is kind of like, now the traffic is a lot more slower at the start of the segment. So gap acceptance model created a lot more congestion that we actually see out there. So it means that the, the normal gap acceptance model. So we see some more advanced gap acceptance model, but this is a very basic gap acceptance model. This is kind of like, if the gap is fine, I'll change it. If it's not fine, I won't change it. So it's a simple gap acceptance model. You can find, of course, more gap acceptance models with the probabilistic nature that will perform better. Then we tested the mobile, and mobile performs a lot better than the basic gap acceptance model. There was a congestion at the same location here between 2 and 2.5. The speed here was fairly low, which was compatible. And there was, however, another congestion here, another on-ramp, which we don't expect to see. Okay, and remember, the seed for these simulations are all the same. So the vehicles are getting into highway all at the same time. So it's just the performance of the models that are different. Then we finally simulated with the approach that I just presented to you, the game theory-based model. With the game theory-based model, we saw a slow traffic between 2 and 2.5 on the ramp. We saw a slow traffic at the start of segment, and we didn't get anything in other places, which was very matched to what we got from the loop detector data. And I think it's a good indication that the model is actually working. Of course, there's more validation, more calibration is required for this system, but the model is working somehow at this level, even with this simplified version. Of course, we expect to, once we add more parameters to the payoff matrices and we calibrate for more data, then the performance gets even better. Next thing we studied was the effect of market penetration rate of connected vehicles to see if the system will work somehow, and to see if the findings of the system is kind of like in agreement with what we expect to see. At 0%, we just saw the result for the speed profile. There's more scatter with gap acceptance model compared to the game theory. And that's what we expected here. So more congestion compared to less congestion here. And that is important to observe. So at a 0%, we already knew that the game theory model, the game theory-based model is performing better. When we go to 50% market penetration rates, our analyses, on the stability of traffic flow and other research, other studies show that once we have a mixed environment, when we have like 50% connected cars and 50% regular cars, we expect to see more congestion on the road. Okay, so that's one of the reasons for that is because we see more heterogeneity in the road. So these cars are not interacting sometimes very well with each other, so we tend to see more congestion. So the gap acceptance model didn't create this. So at 0%, the congestion is higher than 50%. And you move to 100%, you expect to see that, at 100% connected cars, you expect to see almost no congestion, right? So, but gap acceptance model has a different approach. It has very high, a lot of congestion here, and the congestion reduces here at the 50%, and then it increases again. So the scattering fundamental diagram increases at 100% compared to 50%, which doesn't make sense at all. So with the game theory-based model, we saw that at 0%, the system works fairly reasonable. We already looked at it in the previous slide. At 50%, the scatter increases in fundamental data, and once we go to 100%, the flow increases and also the scatter decreases compared to the 50%. So the results was more in line with what we expected to see, but the model has to be calibrated for this data, and hopefully the data will come soon this year, and we should be able to calibrate this model and test it, based on the actual connected vehicle data. So with that, I would like to conclude this presentation. I introduce you a game theoretical-based lane changing framework to model the lane changing behavior in the presence of B2B communications. We went over a calibration approach and we calibrated a simplified model. I should emphasize that this was a simplified model and that was performing well. We expect that a more general model with more parameters performs better. We use a fictitious play-based simulation approach to simulate this model, and also basic simulation results reveal that the model performs better than simple gap acceptance and mobile models. And also, of course, again, additional calibration and validation using new data sets are essential for this process. And thank you so much for your time. And again, thank you all the organizers of this event, and I'm at your disposal if you have any further questions.
Thank you, Alireza. Very interesting.
Very interesting.
Thank you.
I don't know, I got some echoes, but I think we have plenty of time to entertain questions. So if you have questions, you can unmute your computer and raise your questions from the audio system, or you can type on your chat box.
Please ask questions. That's the only way that we can discuss this further. So.
Yes, I have a question, Jack Haddad from Technion. So can I ask Shao now? It's okay?
Yes, of course.
Yeah,
go ahead.
Do you hear me?
Yes.
Okay, good. Okay. So thank you for this nice presentation. You were mentioning that the test study that you tried, the traffic condition is actually uncongested. So my question would be the following. First, why you didn't test it for congested conditions? And second, if the current modeling is not appropriate for congested condition, is the current framework can be extended, and how for congested conditions?
Thank you, Jack. Great question. So no, we didn't test it for uncongested condition. We tested for a congested condition. We didn't test it for the densities near jam density. Okay, so the traffic condition here is a stop and go. It's kind of like a slow and go at this point. Okay, so I think the model will work very well for this level of condition. We haven't tested it for densities near jam density because that is a whole new behavior. So that is something that your question is very valid, and that's something that we need to test before I can answer your question. But
so what I understand that you need two different model behaviors for congested and uncongested regimes.
Well, I wouldn't say that, because like this model works for, excluding the jam densities, this model works for the free flow regime and congested regime all the way until near jam density. Okay, all the way until the second leg of fundamental diagram reaches the zero level for the flow. Okay, so for that part, my own perception is none of our models currently work for that area, because that area involves a lot of forced lane changing, and forced lane changing is a completely different behavior.
Okay. So
I think we need different modeling for that part.
Okay. Thank you very much. There is another question here by.
Yes, I saw that. Yeah, thank you, Danju. Danju says you assume that connected vehicles have a smaller reaction time and a smaller spacing. What if you assume that such improvement doesn't exist and the improvements only comes from lane changing behavior? Very interesting question. Thank you, Danju. Well, of course, the behavior we assume that they have lower reaction time for the car following behavior. Okay, so I think that is specifically important in the lane, gets involved into lane changing because some of our payoff functions were based on the acceleration to avoid crashes, and reaction time can definitely has effect on it. I think the behavior of the model will be very different in that case. However, considering the case that we don't have any V2V communications, the graphs that I just showed you, the speed profiles, in those cases, the lane changing behavior is the same for all cars, and the cars don't have any reaction time. So I assume that the model was performing very, very well. So I assume that the model will perform reasonably well in that case as well. But that is something to test more actually. So I'm not sure if I answered your question completely. Please write that down, and please write it down. I'll just if I haven't answered that completely, and I'll respond. And there's one more question. Okay, you're welcome, Danju. Thank you, Kaveh, for the question. The question talks about how does the error measures you got on US 101 compare with previous lane changing models, Gibbs, etc. Also, why payoffs do not take into account distances, the way target and lead like vehicle. So let me see if I answered, if I can understand your question completely. It says, how does the error measures you got on this one compare with previous lane changing models? So I'm not sure what you mean by error measures, Kaveh. We tested the difference in the congestion term and congestion level, and what would be the travel time actually as well. So those were the measures we used. But if you want to really compare those, the purpose of this paper wasn't to compare the models together. If you really want to see the performance, how they really work based on different models, because we didn't even tested the Gibbs model. That can be a whole new study, and I think it's a valuable study to do. I don't think anyone has. I haven't seen it, at least. I haven't seen a study that compares different lane changing models. Unlike that, we see a lot of those for the car following models. I haven't seen that for lane changing models, and I think that's a valuable thing to do. And your second part of the second question was why payoffs do not take into account distance with target and lead like vehicles. So the distance was somehow considered in the acceleration to avoid crash, okay? Because the acceleration to avoid crash is considered the reaction time and also the distance between vehicles. That's how we consider the distance between vehicles. But you can argue that, okay, you want to have the actual distance, and that is an important factor, and I agree with you, and that can be considered into the system as well. So I think that is a weakness in the simplified model. But as I said, we want it to be simple, but it is somehow being captured, but not exactly as one single and separate parameter. I hope I answered your questions. Thank you. So the near questions, I think he loves some concepts in mobile, which is using acceleration to replace distance. Okay, yeah, thank you for the comment. Appreciate it. Another question. Thank you, Amir, for the question. The decisions on the lead and the target vehicle independent. It depends what you mean by the independent. The two drivers are playing a game, so they're observing the other's decisions and making decisions to based on the other driver's decision. In that regard, they are not independent, but they are doing their own. They're making their own decisions, and this is a non-cooperative game. Okay, so it's not cooperative game. So the two drivers are not cooperating at all in decision making. So from that point of view, it's independent. Yes. There's an argue of why we didn't make this cooperative game, because in some cases it becomes cooperative. So the reality is it's a mix of both of the games, and I haven't seen any study in the game theory. I haven't looked a lot. I should say that that considered both of the games. Okay, so more clarification, I mean, in connected vehicles that could be cooperative. Yeah, I agree with you. Yeah, I totally agree with you. So it could be a game of, of instead of non-cooperative game, it could be a game, a cooperative game between. And the reality is, cooperative games are easier to solve, so and to calibrate. So that will help us actually. So that is something very interesting to test, and I would be more than happy if you are interested to work with you on this. So do we have any other questions?
Yes, I think Jack raised one more. Can you mention something about the computation efforts?
What do you mean by computation efforts? So if I don't have the exact values for that, because a lot of, so at least for the calibration part, a lot of this is being taken care of by software called Gambit, which is very well validated by the community, by the game theory community, but I have no idea what is happening in there. So because solving a game is very challenging, and in reality, we couldn't solve a game until 2001 in a general form. So before 2001, we could only solve games with a specific design and characteristics. It was only in 2001 that someone introduced a method to solve a game. So it is a complicated task, and I don't know what's happening inside that. But I can tell you, it's a slow process for the calibration. For the simulation, however, it is a lot easier. For fictitious play, it's an iterative game. So I choose a strategy, you choose another strategy, and I choose a strategy, you see my strategy, and you react. And then I see your strategy, and I react to, both drivers are trying to make the best out of this game. So it is a very easy process. It's not adding any computational issue. It's just a selection between 2 or 3 choices. It's very easy to apply. It would be good. Yes, it will be definitely interesting to test that to see. I agree with you, Jack. Your questions?
Any other questions? Well, Alireza, thank you for the great explanations and response. It's a very interesting work and very promising. So we know connected vehicles and autonomous vehicles. The problem is not whether they come or not. It's about when they come. But as of now, we don't have many deployed technologies in the real world of those. We have some test bed and pilot projects. And in order to analyze and especially calibrate, validate those corridor level, network level models, what information or from what approach you would expect we can do in order to calibrate the model, compare the theory and the reality. I know it might be, it might be very challenging at this point of view, but do you have any insights about what we can do or what resources we can use as a research community to pursue the calibration of these theories and models?
Yeah, it's a very good question. I can only give you what I think will happen, but that's not necessarily true. So there are 2 aspects into it. One is the design, because we as like transportation engineers aren't the ones that are designing this. It's like the technology companies, the auto industries are the ones that are designing this, and we can only put regulations on it. So that's one aspect. So we don't really have that much control on what would be available, what would happen. So for instance, in this study, we assume that the drivers will know the type of lane changing maneuver, but that is not necessarily true because depending on if he decides to kind of like transmit that data or if we decide to transmit another data. Okay, so that is one kind of issue with these modelings that we are using at this point. In terms of availability and calibration, I think it's not going to be very different. So if you want to test your models, I think right now there are available data. The OMTRI, the University of Michigan, has data available and it's available to public to access it. Okay, so at least for some of the applications, not at the highway level, it's just probably the data. I think the data for 6 or 10 cars. At least for some basic things, you can use that data. Okay, so some of the very basic stuff. Okay, so and I don't think it's going to be anything other than taking baby steps with this technology until it gets more popular. I know I'm just jumping from this branch of the other one, but I think for the calibration process, once we have the data in place, I think it's not going to be an issue at all, because we are going to have more accurate data. First of all, we're going to have the information about the movements of vehicles, and we are going to have information about what messages they exchange. And putting both of them together, I don't think there's something that we can do at this point. And it's just a matter of putting them into the calibration approaches that we have right now. It just needs a small change here and there. I think the calibration process won't be an issue.
Thank you. Appreciate it.
I hope I answered your question.
Yeah, of course. Great. Any other questions? Okay, well, thank you, Alireza. Great presentation again. And I've recorded this video, and I'll send this video later. I'll just when I process it and find a link to upload it. So with this, thank you all again for attending this presentation. And next one will be 2 weeks from now, given by Dr. Shang He at Purdue University. And with this, I hope you all have a good weekend. And we'll see you 2 weeks from now.
Thank you so much. Shao, I will send the slides to you in a few hours.
Okay, sure. I'll share the slides and the video with the community. Okay, thank you.
Thank you. Thank you. Bye-bye.
All right, bye-bye.